Hello everyone, I'm Alba. Welcome to Lecture 4 of Machine Intelligence I. In the last lecture, we learned how linear regression fits a straight line to predict continuous values. Today, we'll move a step further into classification by introducing logistic regression, the foundation for many modern classifiers. Linear regression gives predictions that can be any number from -infinity to +infinity. But in classification, we need bounded outputs, for example, 0 or 1, to decide between two classes. So our goal is to transform the linear output into something that can represent probabilities or decisions. We start with a simple linear score, z equals theta transpose x, that can take any real value. The first transformation is the sigmoid function, which squeezes the infinite range of z into values between 0 and 1. This makes it ideal to interpret as a probability. The second transformation recenters it from open bracket 0, 1 close bracket, to open bracket -1, 1 close bracket, so that the midpoint 0 marks the decision boundary between the two classes. In this view, predictions above 0 mean class 1 and below 0 mean class 0. Now, let's connect this intuition to probability theory. Linear regression outputs z equals theta transpose x, a real number. Logistic regression models the odds, the ratio of the probability of y equals 1 to y equals 0. Taking the logarithm of the odds gives us the logit, which equals our linear output z equals theta transpose x. When we invert this relation, we get the familiar sigmoid, p of y equals 1 given x equals 1 over 1 plus e to the power of negative theta transpose x. This forms the core of logistic regression, linking linear combinations to probabilities. Let's visualize these transformations. First, we plot the linear output, unbounded and continuous. Then we apply the sigmoid, mapping everything smoothly into 0, 1. Finally, we recenter the range to open bracket -1, 1 close bracket, aligning with binary labels. This shows how a simple mathematical mapping turns regression outputs into interpretable class probabilities. Let's now compare linear and logistic regression in practice. Using the iris dataset, we train both models to classify whether a flower is setosa or not. Linear regression tries to predict 0 or 1 by thresholding continuous outputs, while logistic regression directly models probabilities. We then generate a prediction grid to visualize each model's decision boundary. Here you can see the difference clearly. On the left, linear regression produces unrealistic, skewed boundaries. On the right, logistic regression gives a smooth, well-behaved separation between classes. This demonstrates why logistic regression is better suited for classification tasks. In the next lecture, we'll extend this idea further into multi-class classification and softmax regression.